Many teams assume you can build an autonomous AI software engineer simply by connecting a large language model directly to a human command line interface. This is the naked LLM approach. The model is hooked directly into a standard Linux bash shell and told to navigate a raw codebase. This volumetric container represents the model's context window. Standard commands trigger a massive influx of raw text, instantly exceeding limits. The specific code needed becomes obscured by syntactic noise. Humans visually filter noise, but a model evaluates token by token, stalling against the unformatted volume. Therefore, the raw text environments generated for human developers must be explicitly translated into strictly structured, machine-executable formats. Exposing a model to these unmanaged, high-volume human interfaces causes immediate operational failure through context overflow and signal loss. Bridging the gap between model and a machine requires an architectural layer that translates codebase complexity into token-efficient structures. The SWE-agent architecture defines an autonomous agent as the combination of a core language model and its specialized execution harness. This system is designed to read natural language problem statements from GitHub issues and convert them into fully executable software pull requests. This schematic outlines 3 engineering problems SWE-agent must solve. Surrounding the central large language model node are empty sockets representing context exhaustion, execution, and state management. To fill these gaps, the harness introduces 3 structural solutions: context compaction, Docker sandboxing, and an agent-computer interface. By explicitly constraining the computational environment, a highly specialized harness allows a moderately sized language model to execute complex software engineering tasks with higher accuracy than a massive, unconstrained model. The process begins with the problem statement.py module. It ingests the raw text of a GitHub issue and sets the initial parameters for the coding task. The system then enters the main trajectory loop, which acts as the core state machine governing the entire lifecycle of the agent. Instead of letting the model generate continuous, open-ended output, this loop restricts the interaction to a strict turn-based execution cycle. This circular flow diagram tracks the mechanics of that trajectory loop. For every turn the agent takes, the system actively monitors and increments a paired numerical counter, enforcing precise step limits and token budgets against a hard predefined ceiling. Without these constraints, a model will often fall into infinite hallucination loops, repeatedly attempting failed commands. By enforcing budget limits, the system triggers a gate that forces the model to either drive a definitive state transition or terminate the attempt entirely. The trajectory loop structures the interaction, transforming passive text generation into a controlled, forward-moving computational process. To execute commands within that loop, SWE-agent replaces the standard Linux shell entirely with a bespoke agent-computer interface, or ACI. Defined within the tools.py module, the ACI strictly prohibits the language model from utilizing raw bash commands. This side-by-side matrix shows why standard commands fail compared to the ACI. On the left, a standard file output unspools infinitely downward. On the right, we see the ACI open file command. It returns a strictly bounded numbered block containing exactly 100 lines of code. This mechanism is called line windowing. It smoothly paginates down to isolate exactly what the model needs to evaluate without overwhelming its token limits. To navigate within this isolated window, the ACI provides specialized go-to line and scroll down commands. The model moves through the codebase sequentially without forcing the system to reload the entire file. When searching for specific variables, the ACI uses a custom search_dir command. Instead of generating a massive recursive output like a standard bash grep, it returns concise, formatted pointers to the relevant files. For making actual changes, the ACI relies on a custom edit command. This forces the model to specify precise string replacements within the defined window, rather than attempting to rewrite entire files from scratch. This toolset limits the model's focus to the specific variables and syntax required for the fix, preventing the attention loss that occurs with unmanaged data blocks.
The ACI dictates what the model is allowed to see, rigorously protecting it from the noise of what it shouldn't see. Retrieving information is only half the problem. Executing untrusted code autonomously introduces massive risk. If an AI alters files or updates dependencies directly on a host machine, it ruins benchmark reproducibility and exposes the core system to severe security vulnerabilities. To enforce a hard boundary between the agent and the host, SWE-agent utilizes 2 components: SWE-env.py, and swerex. Look at this layered schematic mapping the execution boundary. The language model generates an ACI command. That command must pass through an impenetrable wall managed by swerex, which routes the execution directly into a confined Docker container. There are no return paths to the host, except through a single restricted output channel. By running every command inside a container, the system guarantees a consistent, identical baseline environment for every single trajectory run, erasing all modifications between attempts. This sandboxing gives the model absolute freedom inside the container. It can compile code, it can corrupt files, and trigger fatal kernel errors without risking any damage to the host architecture. Autonomous iteration requires a safe environment to fail. Docker isolation provides the essential blast radius containment, allowing the model to relentlessly test its solutions. As the model executes these iterations within the Docker container, it generates a long sequence of ACI commands, test runs, and system observations. This chronological trajectory history grows exponentially with every turn. The context assembly module aggregates the system instructions, the outputs from the ACI tools, and these historical observations into a single prompt. By turn 20 or 30 of a complex software patch, passing the entire raw history back to the language model will trigger an immediate token limit exhaustion. This visual tracks the history compaction mechanism. The vertical stack represents the agent's complete memory history. As the stack grows dangerously tall, the system takes the older blocks at the bottom and compresses them into a single, dense summary block. This truncation process explicitly discards the noisy step-by-step logs of previous failed commands. It persists only the essential memory markers the model needs to complete the current software patch, remaining safely under the token limit line. Context assembly functions as the agent's short-term memory manager. It sacrifices perfect historical recall to maintain operational token efficiency. With the context managed and the commands executing safely, how does the agent actually confirm it has resolved the GitHub issue? Verification is strictly empirical. The agent must run explicit test commands using the ACI within the isolated Docker boundary. If the test fails, the error output is fed directly back through the context assembly. The model reads the failure logs and generates a new ACI edit command to correct the logic. The termination condition is only met when the system receives a successful test output. That verified signal prompts the agent to format its final changes and submit the completed software patch. Strict, objective, test-driven verification guarantees the output. The system relies entirely on compiler feedback to translate a string of generated text into a proven working pull request. This macro-level flow diagram traces the complete SWE-agent architecture. The system ingests a GitHub issue, structures the intent into ACI commands, executes them safely inside the Docker sandbox, manages the ongoing memory through context assembly, and finally verifies the results into a definitive patch. Directly exposing an LLM to standard bash tools creates an immediate, mathematically guaranteed failure in context and attention. The intelligence of the system is distributed across the entire architecture, rather than existing only within the weights of the foundation model. Operational intelligence emerges directly from the harness. It is the architectural constraints that successfully bridge the gap between natural language reasoning and strict software execution. Advancing autonomous engineering requires building specialized, machine-optimized boundaries. The computational environment you construct for an AI dictates its capacity to succeed.